Okay, so we talked about what to do if we're looking at plus or minus 1 standard deviations, plus or minus 2 standard deviations, and plus or minus 3 standard deviations. However, it's natural to be asking about other values as well, right? So not only are we interested in plus or minus 1, plus or minus 2, and plus or minus 3 as our z-score, getting normal probabilities corresponding to that, we might be looking at something like 0.57. Okay, and this probability that z is less than 0.57 is essentially asking what's the probability that some normal random variable generates a value that is 0.57 standard deviations above the mean or less. Okay, so we can use R to tackle such a question, and so we might use this Pnorm function. This is actually the handy function we want to be using, and all we do is pop in a z-score, and out will pop a probability. So you might guess this P in Pnorm actually does stand for probability. In goes a normal distribution value, and out comes a probability. One of the functions that comes in with the Mosaic package is this enhanced version of the Pnorm function. All you have to do is pop in an x in front of Pnorm, and then you get the added capabilities of basically not only getting the left tail probability, but you also get a right tail probability. And you get both of these shown together on a really nice density curve. Okay, so what do we do then if we are dealing with a more general normal distribution, not just the standard normal distribution? How do we use Pnorm in that case? So one thing that's really, really handy about the normal distribution, which we alluded to before, is that it is scalable. That you can take any question about any normal distribution and turn it into a question about the standard normal distribution. So the way we do that is we go through this process of standardization, which is just a fancy way of saying calculating a z-score. Okay, so to calculate the probability that x is less than 3.5 here, we are simply converting that 3.5 into a z-score by subtracting away the mean, dividing by the standard deviation, and then, just making some assumptions to give us some concrete numbers to pop in. We can then pop in that new z-score into R to get our values. You actually can specify the mean and the standard deviation into Pnorm to get a probability directly without having to do that standardization process yourself. So you can see what I've done here is I've popped in 3.5 as my first argument. I've then popped in my mean and my standard deviation as subsequent arguments. And then R basically will do that same calculation for me without having for me to do the z-score conversion. Okay, so let's take a moment and go through some actual exercises just to make sure that we know how to apply this to some real questions. So I'm going to do this in a blank slide. For this first one, probability that x is equal to 3.5. So how do we figure this out? We're going to draw our normal distribution. It's going to be centered around 3. So let's imagine 3.5 is right here. Well, the probability that x is equal to 3.5 is basically asking us for the area that corresponds to that line. Right? Because we talked about how probabilities for the normal distribution relate to areas under the curve. So as we learned in calculus, a line does not have any area, and therefore the probability here must be 0. In fact, what we've just seen is some anecdotal evidence that any continuous distribution, meaning any distribution that defines a positive density for a range of numbers on the real line, must give 0 probability to any specific value. Okay, so you can get probabilities that are greater than 0 for ranges, for intervals, but you're always going to get a probability of 0 when you're asking the probability of x being equal to a specific value. So definitely bear that in mind. So this line of reasoning also holds through when we consider the probability that x equals 3, okay, because in this case, we are still looking at a vertical line. Now, that vertical line does appear in the exact center of our histogram or of our density curve, so you might think that's a pretty frequently occurring value because 3, after all, it is our mean. However, what this is telling us is that while we believe the mean to be around 3, we're saying that values near 3 are more likely than values that are far away from 3. But we're still saying that the value of exactly 3 is going to be very, very unlikely. C, we have the probability that x is greater than 3.5. So now no longer are we looking at a single line, we are looking at a region. So once again, here is 3. Let's imagine here is 3.5. Then we are asking for this entire shaded region. So first of all, we have to note that Pnorm always gives you left-tailed probabilities. So we're going to have to rewrite this into a left-tailed probability. So 1 minus the probability that x is less than 3.5. And then I'm going to do my conversion into a z-score by doing 3.5 minus the mean of 3 divided by the standard deviation of 2. And that's going to give me 0.25. So finally, I'm just going to pop 1 minus Pnorm of 0.25 into R. And so as you might have guessed, if you had just jumped straight from the 3.5 into the conclusion by making use of the fact that Pnorm can handle non-standard values, you could just do 1 minus Pnorm of 3.5, comma 3, comma 2. So if you do this calculation, what you're going to find is that the answer is 0.4013. Next one, what about the probability that x is less than 3? Well, hopefully you're not getting your calculator out for this one because, remember, 3 is the mean of our distribution. Here is 3. So what that means is we should have 50% probability below and 50% probability above simply due to the symmetry of the normal distribution. So the answer to this is going to be 0.5. Now what about the probability that x is less than 1? Well, certainly you can pop this into Pnorm again as well. So we can say this is equal to the probability that z is less than 1 minus 3 divided by 2. Okay, and that's going to be the probability that z is less than negative 1. And so all we need to do is Pnorm of negative 1. If you do Pnorm of negative 1, what you're going to get is 0.1586, and that would be our final answer. Just a note, because we are therefore just looking at, a z-score of negative 1, we're looking at the probability of being below exactly 1 standard deviation below the mean. We could actually apply the 68, 95, 99.7 rule to help us here. So I would challenge you guys to take a look at how you might do that. You should get an answer that is reasonably close to 0.1586. Differences are going to be due to rounding. Okay, so now let's go back to what we had from example 1, which is looking at the 3 exams you took in chemistry, biology, and economics. So suppose you're then wondering how those z-scores that you computed correspond to actual percentiles. So what percent of the class scored below you in each of those classes? We now have enough information to answer that question. However, we're going to have to assume that a normal distribution applies to the scores in each of those 3 classes. So if you remember, for chemistry, you had a z-score of negative 0.2. So what we want to know is what's the probability that z is below negative 0.2. We can simply pop this into R in this way, and we're going to get 0.42. And that just says that 42% of the data lie below a z-score of negative 0.2. We can do the same thing for biology, and here we would find that the Pnorm for our z-score of 1.4 is 0.92. Okay, and finally for economics, we would have Pnorm of 1.25, which translates to 0.89. So these are the numbers we're going to stick with. And again, you can see that in biology, you did the best under a normal distribution because you scored better than 92% of your classmates. Now, what if we wanted to go the other way? So we know how to find probabilities now when given a specific value along the normal distributions, but what if we wanted to go and ask, well, what value would have corresponded to the 90th percentile of the class? How would we actually do that? In R, we have a very similar function to Pnorm. In fact, it is called Qnorm, where Q stands for quantile. And all we have to do here is pop in a value between 0 to 1, and we're going to get the actual percentile or quantile corresponding to a standard normal distribution. So for example, if I'm looking at the standard normal random variable and I want to ask, if I'm drawing this normal random variable and I want to find what point do we have 90% of the data below, so what is this vertical line? I simply pop in 0.9 into Qnorm and out comes 1.28, and that corresponds to the value here on the x-axis. So, given that information, can we then go back and calculate the 90th percentile for each class? Okay, so we already know the 90th percentile for the standard normal distribution, and we know this to be 1.28 based on our notes. I'm going to call this Z star. So now what I'm going to try to do is figure out what the actual scores in each of these classes would have to be to give me z-scores of 1.28 across the board. So once again, I'm going to start with chemistry. And 1.28, setting that equal to x minus the mean of 86 divided by 5. I'm just going to use some basic algebra, and I'm going to find that a score of 92.4 would correspond to the 90th percentile. For biology, very similarly, I'm going to do 1.28 is equal to x minus 70 divided by 5, and that gives me x is equal to 76.4. Then finally, for economics, I have 1.28 is equal to x minus 90 divided by 4, and so x ends up being 95.1. So not surprisingly, in my hardest class of biology, I did better than that 90th percentile, which makes sense because I scored at the 92nd percentile. And you can see that, of course, here being that it's so hard, the 90th percentile is very, very low.